Good afternoon. My name is Chris Koh.
My name is Kavi Manjal.
I'm Nicholas Sang.
I'm Olivia Yao.
And I'm Billy Zhang.
Our group research project is the digital 3D printing of soft robotic devices.
Alright, so just a brief overview of what we're going to be going over today. First, we're going to take you through a background of some of the just major terms, applications, and processes that relate to our research. Next, we will move on to creating and testing solutions. We will take you through the procedure and methods as well as the data we collected. Next, we will move on to printing and flexing, which is the second part of our research, which is the creation and printing of the actual 3D models, as well as testing them for flexibility. Then we will analyze our results and as well as the errors that took place in our research. We will conclude with our major findings as well as future research ideas, and we will also do our acknowledgements and references. So we had three major objectives in relation to our research experiment. The first was to explore the different materials used in 3D printing. The second was to find the optimal ratio of these materials in printing 3D soft robotics models. And our final objective was to find or attempt to create bending in basic structures that we created.
3D printing is additive, meaning that materials are printed in a layer-by-layer process to create a physical object. In contrast to a stereotypical metal robot, in this project we investigated soft robotics, in which we use pliable materials to create movement. In addition, swelling is the absorption of a liquid to create movement in a soft robot, or flex.
So the subject of our research has far-reaching applications. In general, 3D printing is becoming very popular because of its ability to print on a very small scale with precision, as well as its ability to print on-demand and individualized items. This eliminates the need for mass production as well as storage. Also, 3D printing is becoming increasingly available to the consumer, which is an aspect we took advantage of in our research experiment. Specifically with soft robotics, there are many potential applications in the medical field due to the soft robot's ability to perform on a micro level without hard motorization of any kind. 3D printed soft robotics are also very useful for modeling animal and plant movements, such as the Venus flytrap, the octopus, as well as the squid.
One way to create soft robotic movement is through the swelling of hydrogels. The hydrogels that we use are chains of polymers that react and swell when exposed to acetone. Although water can produce the same result, acetone dries up much more quickly and thus provides us more efficient and reliable results. Photopolymerization is needed to print these special hydrogels. Basically, photopolymerization is the process whereby UV light emitted from the projector solidifies the liquid printing material known as resin into a solid, more stable structure.
In this project, the method of 3D printing that we used was projection microstereolithography. In this method, 3D models are first created on a computer-aided drafting software. In this case, we use SolidWorks. These models are then transformed into digital cross-sections in the form of black and white images on PowerPoint slides. The PowerPoint slides are projected through a lens, which allows the light to converge instead of diverge, and these images are mirrored onto a stage. The white PowerPoint images solidify the resin, or printing material, and after the material hardens, the stage can be moved down 160 micrometers, and the process can be repeated until the print is finished.
So on to what we actually did when we were operating the printer, which we created ourselves. So first and foremost is the most important part, which is where we focus the actual slide. The first slide of the PowerPoint presentation that we shine onto the stage is of red X's and lines. And the reason why the lines and X's are red is because you can't photopolymerize any of the resin with red light. Only white light is intended not to do that from the projector. It is also, at this point, it's also necessary to level out the stage with a small liquid level. So after that, the resin levels are raised so that they barely cover the surface of the stage, at which point a red outline slide is shown just to double check that everything is set correctly and there's enough space on the stage for the actual print to proceed. So following this is the first exposure to white light. So this first exposure goes on for approximately 150% of the normal exposure time. And this is because we want to make sure that the print is firmly connected to the rest of the stage so that no unwanted moving or misalignment of the prints go on as more levels and more layers are projected onto the resin. So following this exposure to white light, the stage is lowered by a quarter turn of the knob on the stage assembly, and this induces a 160 micron drop. This is repeated over and over again until finally the print is completely finished and all layers are done. At which point the print is removed with the help of a small razor if necessary. It is then rinsed out in acetone to get rid of any unwanted, uncured polymers. And then following that, it is cured in a dark container filled with more acetone. And here you can see on the left is a picture of a small Taj Mahal that we printed. It's also on the right, you can see actually the image of the small piano that we are passing around. Both these are approximately 1 centimeter in height.
So we used a variety of chemicals to find the best ratio between PEG-DA and PEG that would swell and function properly. So PEG-DA 700 is a hydrogel that gels quickly at room temperature and when exposed to UV light from the projector. PEG 200 is a porous polymer that induces high osmotic pressure within the solution. And the photoabsorber, known as Sudan 1, prevents unwanted curing of excess resin that might be exposed to stray UV light from the projector. And finally, the photoinitiator, known as Phenovis, reacts to the UV light, begins photopolymerization, which, as mentioned before, is a process where UV light solidifies the liquid resin into a solid.
So, briefly, as just mentioned, the first two chemicals that were mentioned were PEG-DA 700 and PEG 200. These are the two primary polymers of our solution, and these are the two experimental variables that we chose to alter to see which ratio would be best for our experiment, which we'll explain shortly. So the other two were controls. We kept the photoabsorber and photoinitiator at strict weight percentages of the entire solution, where photoabsorber was 2% of the entire solution by weight, and photoinitiator was kept at a strict 0.06% of the entire solution. And here there are a couple pictures of us preparing some slides for the swelling ratio test, which is what we did to find which ratio produces the most amount of swelling. So what we did is we produced 11 samples of 1 millimeter thick resin. And these 11 samples all had different ratios of PEG-DA to PEG. And so these ratios range from 10 to 0 to 0 to 10 correspondingly, increasing in integers. So what we did was, once dry and completely cured, we took small discs out of each one of these resin samples. So what we did was we measured the diameters of these discs and then soaked all of them in acetone for a set amount of time. After the small soakage period, we took them out and remeasured their diameters, and we would observe which ones of these had the most amount of swelling.
We compiled this data into a table of values for each solution ratio. Important to note on this slide is that the extreme ratios 10, 0, 9, 1, 1, 9, 0, 10, we're not able to collect data for, and we will explain why soon. Also, for reference, the swelling ratio is the ratio of the wet or swollen diameter to the dry or non-swollen diameter. We further analyzed this data into a couple of graphs. This one shows the dry diameter and the wet diameter. The dry diameter, as you can see, remains about constant as PEG percentage increases, while the wet diameter increases as PEG percentage goes up. And to put it even more simply, we graph the swelling ratio against PEG percentage, and again, there's a very clear increase.
So the second thing that we chose to pursue was actually creating movement in a small portion of soft robotics. So what we did this was, first we created a small channel with the help of CAD, or the computer-aided drafting program. So what we did was this is just a short section of what we created, and it's essentially a rectangular prism with a small trapezoidal prism cut out of it. And this is to induce capillary action once in contact with acetone. Capillary action would draw the acetone up one side of the channel, produce swelling via absorption in that one side, and thus produce flexing because of the uneven absorption of acetone. So in the center image, you can see the actual print that we made, the actual channel that we made. Again, it was only about 1 centimeter in height, but it took roughly 100 to 120 layers to complete. And then finally, on the right-hand side, you can see a microscopic cross-section of the actual image, or the actual channel. And so you can see the several vertical stripes are the small distances between the actual layers, each layer being about 160 microns thick. Whereas the large horizontal stripe is actually the channel that we created and designed using CAD software. So we did this so that we could conduct the channel flexing test. The channel flexing test was pretty much to see which one of these ratios of solutions would create the most effective swelling and thus flexing. So we did this by anchoring one part of the channel to a small mechanism, which you can see pictured here in these two figures, and then we dipped the other end of it into acetone. Once in contact with acetone, it would flow up one side of the channel and thus induce swelling and flexing, and we would be able to visually observe which one of these solutions would have the greatest amount of flexing in their final prints.
we first initially designed a channel on SolidWorks to test flexing, and after this experiment, we also designed a grabber. The grabber, as you can see on the lower left, contains 3 channels attached to a hexagon base. When in contact with acetone, the channels will bend outwards, and as the acetone evaporates, the channels will start to return to their original position, allowing the grabber to pick up small objects.
So for our experiment, we encountered several unfortunate errors, the first of which was that we had incorrect amounts of photoabsorber and photoinitiator to our first sample solution. This resulted in the sample solution curing too fast, which made our final material useless for our purposes. The second problem we encountered was with the sample cutter. We used a sample cutter to cut discs out of the final material, and we then measured the discs for the diameter and the swelling ratio of the materials. The sample ratios that we had most problems with were the 0, 10, 1, 9, 10, 0, 9, 1 sample ratios. The 0, 10, and 1, 9 ratios, they ended up being too soft, so movement and measurement were unrealistic. While the 10, 0, and 9, 1 sample ratios ended up being extremely brittle, so when we tried using a sample cutter to cut discs out of it, the discs ended up shattering, so that made our measurements unreliable as well. As for our results, we've concluded that the more PEG we add to the solution, the softer the final material will be, while the more PEG DA we add to the solution, the harder the final material will be. Because PEG also makes the solution more porous and flexible, that's why the final material is soft. Because of PEG's softness and flexibility, along with PEG DA's stability, it's crucial to have a healthy balance of the two. So at a 5:5 or 1:1 ratio, it's optimal to keep it there, and flexing is best expressed at those ratios.
Just to restate, our original objectives at the beginning of this research were to 1, explore different printing materials, 2, to find the best ratio between these printing materials, and 3, to design a structure that uses soft robotics to create movement. And although we accomplished our first 2 goals, we have still yet to work on our third goal. We found a strong correlation between PEG DA and PEG in the ability to swell, and we found that a 1-to-1 ratio was of PEG DA to PEG was optimal to allow the structures to retain their stability, but also to be able to swell and flex.
If we were to continue our studies, we would further analyze the ratios of PEG DA and PEG and find out which would be the best one to work with. Furthermore, we would look into different polymer structures and find out which is the most stable when exposed to acetone. Finally, we would look into the durability of prints in real-life applications such as open heart surgery and nerve reconstruction.
We would like to express a thank you to our project mentors, Professor Hoan Lee, Daehoon Han, Lucas Liu, and Wang Ying Choi for all their help in the lab.
We would also like to thank our residential teaching associate, Eamon Collins, for his guidance and assistance throughout our research experiments, as well as his help with editing our research paper and our presentation.
We'd like to thank Dr. Eileen Rosen for making all of this possible.
And of course, we'd like to thank Dean John Patrick Antoine for his kind support and guidance throughout this entire project, as well as his securing of all the necessary materials to make our research possible.
And we'd like to acknowledge our sponsors for making this program possible.
Here are the references that we used for our presentation and our paper. Thank you for your attention today, and we will now open the floor up to any questions you may have. Shravan?
So I know you mentioned you had a very strict amount of photoabsorber and photoinitiator that you added. What determined that amount and what happens if you add too much?
So the function of the photoabsorber is pretty much to limit the amount of stray photopolymerization. One issue that we actually had when we were conducting our prints was that once in a while we would find that stray light, it could be anything from a window to a desk lamp to a room light, would create a lot of unwanted photopolymerization. So pretty much what the photoabsorber did was it kept that polymerization that we didn't want. It kept most of it out. Of course, it did not limit the amount of actual bright white light polymerization because that is really concentrated light that's coming from the printer. And it's kept at that amount because too much, obviously, it's going to actually start affecting the polymerization that we want, whereas too little is going to allow too much straight polymerization. As for the initiator, it's the same idea except almost in reverse. If you have too little initiator, you won't start any of the reactions caused by the bright white light. Whereas if you have too much, it's going to make the prints or the resin even more sensitive to that straight polymerization. And also, actually really quick, I forgot. One time early on in the project, we were conducting one of these prints, and before we knew, we had put way too much photo initiator in it. And when we actually tried to print it, the entire block of resin came out solidified. So not like actually the image that we wanted, but the entire stage was covered in a giant block of polymerized resin.
What happened was this usually occurred about halfway through our experiment, which was very aggravating. But it was actually a pretty simple fix. What we realized was that the stage mechanism that lowered the stage would actually end up going down into the metal base of the stage and jam there. And so what we did is we were able to hold that mechanism and then reset it by spinning the dial so that only that mechanism moved up and not the stage itself. And that way we were able to continue printing.
Any more questions? Nick.
What's an example of current uses of soft robotics like research are doing?
So the most intriguing use of soft robotics right now is research being done into creating heart valves or valves in general in the body using a series of channels. So you would have one channel, let's say, going this way, and 3 more going in the opposite direction or perpendicular. And the ones that are perpendicular would swell and contract in order to allow that main valve to open, like they would act as valves and create opening and closing of that, say, vein or artery, that kind of thing.
Also, another application it's referring to the growth and development of cells. So, because of the accuracy that you can achieve with microstereolithography on the micrometer scale, you end up having the ability to print these incredibly small lattices upon which cells of your choice, which can potentially be nerve cells, are able to grow, and you can direct their growth a lot more easily than you could have on any other printed surface or any other created surface by other means of production.
And one more application of this, as I said earlier, is modeling animal and plant movement. And so far, they haven't been able to exactly mimic a certain species, but they have been able to create animal-like structures that move, that have acetone channels attached to like one leg. And when they release acetone, the legs move so that the entire model of the animal moves forward.
Any other last questions? Yes.
I know you said you use projection microstereolithography for printing. What specific reasons do you consider for choosing this method over other printing methods?
So the most common type of 3D printing is extrusion 3D printing, which is kind of like if you've seen decorating a cake, like piping frosting onto a cake. In this case, we use projection microstereolithography because it's accurate to a very small scale. And in addition, you would notice that we use very specific materials because they needed to be hydrogels in order to swell and move properly. And projection microstereolithography allowed us to print with these materials without damaging the chemical integrity.
And another way, another reason why microstereolithography is really accurate is because where you look at extrusion, the resolution of it is limited by how small the actual head, how small the actual nozzle that it ejects the polymer onto the rest of the print is. Whereas the limit to microstereolithography is the actual resolution of the projector, which if you look at it, they're off-the-shelf projectors. You can find them, you can use practically any one you want as long as it fits your assembly. So whereas you would get like a full-size screen like this, imagine this condensed down to the size of practically an inch across, and that's each pixel is going to be how far your resolution is.
I believe we're out of time for questions, so give one more round of applause.